Okay, we are going to start off our year by talking about functions and their properties. So essentially, let's just say that you had a nice, beautiful house in McKinney. And if I said to you, describe this house, you may say it's 2-story, it is brick, it's in McKinney, it has 3 bedrooms, it has 2 bathrooms, it has 2,000 square feet, and you could describe your house. Essentially, what we're going to do is we're going to look at various functions and we're going to describe them. We're going to say, well, its domain is this, its range is this, it has a certain type of boundedness to it. It increases sometimes and it decreases at other times. It has some symmetry involved. It's continuous, or maybe it's not continuous, so we'll talk about a function's continuity. And we'll talk about whether it has asymptotes or not. So these and other things, these are going to be the ways that we can describe any function given to us, just like we would describe anything else. So let's get started with domain and range. Okay, we're going to talk about the domain and range of a function. And when we talk about a function's domain, essentially what we're saying is what are all the x values that we are essentially allowed to plug in to a function, without violating these 3 rules. Number 1, you cannot divide by 0. Can't do that in math. Second thing, you cannot take the square root of a negative number. Third, you cannot take the log of 0. Oops, that's messy. Can't take the log of 0, or you cannot take the log of a negative number. These are the 3 rules that you cannot violate in math. And so if you are not violating any of these 3 rules, the domain is automatically negative infinity to infinity, or all real numbers. Let me repeat that. If you don't see a division sign in the function, if you don't see a square root anywhere in the function, and if you don't see a log anywhere in the function, you can automatically deduce that the domain is all real numbers, because these are the only 3 rules that you absolutely cannot violate. All right, so the idea that you want to do anytime you have a square root involved, you're going to want to take whatever's underneath the square root and set it equal to 0. Here's the reason. 0 is the first number that you are allowed to take the square root of. You can take the square root of 0. It is 0. But you can't take the square root of a negative number. So you're going to take whatever's underneath the square root and set it equal to 0. When you do that, you're going to get x equals -3. At this point, you're going to put whatever number you get, you're going to put it on a little number line. And then you're going to test a number to the right and to the left of that number, plug it into the function, and then ask yourself a very simple question. Am I allowed to use that, or am I not? So let's say we pick a number bigger than -3, like 0. Okay, 0 plus 3 is 3. Square root of 3 is a positive number, check. So we will check that. But if I plug in a number smaller than -3, like -7, -7 plus 3 is -4. You can't take the square root of a negative, so you cross that out. And what you'll put is a bracket, -3 all the way to infinity. So this whole region right here is valid. You do want to put a bracket on -3 because you're telling yourself, yes, I can use -3. -3 plus 3 is 0, and I can take the square root. Can take. Very important, because students always ask that question. You can take the square root of 0. All right, so now let's look at letter B. And what do we see here in letter B? We see 2 rules being violated, a divide by 0 and a square root. So we're going to take what's underneath the square root, which is just x, and set that equal to 0. Well, that just gives us 0. Then we're going to take the denominator and set that equal to 0. And we get 5. We're going to call those our two special numbers, 0 and 5. So now we're going to make a number line, put 0 there, 5 there, and let's go ahead and plug in some numbers. So if I plug in a number bigger than 5, like 10, I will have the square root of 10, which is a positive number, over 10 minus 5, which is 5. That's a positive number. Check. Now, something between 0 and 5, like 3. Square root of 3, still okay. 3 minus 5 is negative 2. It's okay to have a negative on the bottom, just can't have 0 on the bottom. So, check. Now, something less than 0 is not going to work because you can't take the square root of anything negative. So, that's going to be an x. Now, when you write your domain, it's going to look something like this. Bracket, 0, and all the way up to 5, and you have to put a parenthesis on 5 because 5 minus 5 is 0. You cannot divide by 0, so you can't use 0. So that's how do we denote can't use? By using a parenthesis. And let me go ahead and erase a little bit here. So we'll continue and we'll put 5 to infinity. And so there is your domain. Not so concerned right now about the range, but we do want to focus on the domain. All right, let's try another example as well. All right, so this is so critical that we want to make sure that everyone understands how to figure out a function's domain. All right, so we see a square root situation here, a square root situation here, and we have just another factor on the bottom. So once again, we're going to take whatever's underneath the square root, and we're going to set that equal to 0. When we do that, we get negative 3 halves. We're going to take this x minus 1, set that equal to 0, and we get x equals 1. Then we're going to take the denominator and set that equal to 0, and we're going to get x equals 8. So these are our three special numbers. And so now we're going to make a number line. And on this number line, we are going to put these three numbers. So we've got negative 3 halves, and then 1, and then 8. And all we do now is just check a number in each region and see if we can use it. So let's pick a number bigger than 8, let's say 10. Plug in 10. It's not important that you get the value, just you have to ask yourself, can I use 10? Well, 23, square root of 23 is positive, so yes, I can do that. 10 minus 1 is 9, square root of 9 is 3, 10 minus 8 is 2, yep, positive, check. All right, let's pick a number between 1 and 8, let's say 4. Okay, 2 times 4 is 8, 8 plus 3 is 11, check, I can take the square root of 11, no problem. 4 minus 1 is 3. I can take the square root of 3 because it's still positive. Check. 4 minus 8 is negative 4. Hey, I can have a negative on the bottom. No problem. Check. All right, let's pick a number between negative 3 halves and 1. The easiest one I can think of is 0. So if I plug in 0 on the top, I get square root of 3. That's okay. But if I plug in 0 here, I get negative 1. I can't take the square root of negative 1. So as soon as it fails for any part, the whole region fails. All right, now clearly, if I plug in, if 0 failed, then something less than negative 3 halves is also going to fail, like negative 10. That's going to make this a negative 11. So that's going to fail as well. So your domain is now going to be, now you have to be very careful right here. Do you use a bracket or a parenthesis at 1? Well, let's see. If I plug in 1, 1 minus 1 is 0. Can I take the square root of 0? Yes. But can I have 0 on the denominator of a fraction? No. So therefore, I have to put a parenthesis. So I put 1 to 8. Once again, I can't use 8 because that's going to give me 0 on the bottom. So parenthesis in union with parenthesis 8 to infinity. And there is how you would find the domain of a function. Okay, the next characteristic that we want to talk about as we continue with how to describe functions is a function continuous or not continuous? A better question may be, does it have a discontinuity in it somewhere? All right? And essentially the idea here is anytime you have to, here's the key, pick up your pen or pencil. Anytime you have to pick up your pen or pencil to continue to sketch a graph, that means that graph has what's called a discontinuity in it of some kind. And we are going to talk about three of them. The first is what's called a removable discontinuity or a hole. And we call it a removable discontinuity because it looks like a point has been removed from the graph, so that if you were to plug up that hole, it would then be continuous. So let's just see if we can graph this. Now, right now, it's not as important that you know how to graph it, but we're going to practice and get a head start. So we're going to factor the top and bottom into x plus 2, x plus 1, and then x plus 2. Okay, so we can see here that we have a common factor on the top and bottom. That's going to cancel. And we learned from Algebra 2 that anytime you have a factor on the top that cancels with a factor on the bottom, that's going to give you a hole on the graph. So after we've canceled these factors, we can essentially say f of x is the same as x plus 1 because the x plus 2's are gone. So there is a hole at x equals negative 2. We get that from setting the factor that canceled equal to 0. Now, to figure out where the hole is, you plug in negative 2 into the existing function. Negative 2 plus 1 is negative 1. So there's a hole at negative 2, negative 1. So maybe over here, we'll go left 2 and down 1, and we'll put a hole right there. All right, and we will sketch this function. This is just a linear function with a slope of 1 and a y-intercept of 1. So it looks something like that. And so we can see that there is a removable discontinuity or a hole. So as I'm sketching this, I have to pick up my pen and then sketch it again. So this is the first type of discontinuity that we're going to look at. And at this point, all you need to be able to do is name it. Okay, the second type of discontinuity that we want to basically be able to name and identify is what's called a jump discontinuity. And so let's say we have a function that looks like this. And let's say it stops here, and then it starts again here and does something else. Well, notice this is a pretty simple one. I had to jump from here to continue drawing the function. So that's called a jump discontinuity. So when you see this little gap, just make sure you identify it as a jump discontinuity. The third type is called an infinite discontinuity or a vertical asymptote. So once again, we learned in Algebra 2 that you cannot divide by 0. So what number would cause you to be dividing by 0? 4. 4 minus 4. So x cannot be equal to 4. So therefore, we put a vertical line at 4. 1, 2, 3. We put a vertical line at 4. That's called a vertical asymptote. And the equation of that line is x equals 4. And later on we'll learn how to find the horizontal asymptote, but you probably remember the Bobo, Bosco, Botno clowns from Algebra 2. We see that the powers are the same, x to the first, x to the first. So that means you divide the coefficients in front of these letters, 1 divided by 1. So there's your horizontal. All right, so essentially what you have is a graph that looks like this. Now once again, right now, we're not assuming that you know how to graph these, but you can see that anytime there's an asymptote, the function is going to be going up to infinity on one side and down to infinity on the other side, or sometimes it'll both go up to infinity or whatever. So that's why it's called an infinite discontinuity, because very close to this asymptote, the function is going up or down to infinity. Okay, so let's talk about another property, and that is whether a function is increasing or decreasing or a little bit of both. So an increasing function is pretty simple to identify what an increasing function is. That's simply a function that as you go left to right, like you're reading a book, actually, let's make it like this. As you go left to right, like you're reading a book, the function is always going up. All right? So that's an increasing function. Decreasing function is clearly a function that is always going down. I guess that looks like it's going up for a moment, so let's make it really always decreasing, always going down. So that's an increasing, decreasing function. But most of the time, you're going to be asked to find intervals where a function is increasing or decreasing. So let's actually draw a couple examples here. And so let's say we have this function like that. All right, some sort of cubing function. Now, the key that I want you to write on your notes is anytime you are using interval notation, this is extremely important. You only are using x values only. Use x values only. So what you're essentially saying is this function is increasing from this x to that x. So let's just say there's a maximum point there and there's a minimum point right there. Talk about those tomorrow. But let's say the maximum point occurs when x is -1. And let's say the minimum occurs when x is 3. So let's say we were describing when this function is increasing. You will say this function is increasing from when x is -infinity. So in other words, when x is -infinity, this function is increasing until x is -1. Now you have to say, okay, when is it increasing again? It increases again when x is 3. Notice I'm not using the y coordinates at all. And it continues to increase as x moves towards positive infinity. So there is the increasing. Decreasing, well, it only decreases from here to here. So it's going to decrease from -1 to 3. And we don't use brackets on these. We'll just say we use parentheses. So that is the idea. Let's do another one here. Let's say it looks something like this. And there's our function. So let's say we have that point there. Let's make that -2. Call that point there. We'll make that happen at x equals 1. And then we have another minimum point when x equals 4. So if I said, where is this function increasing? You'll say, well, it's increasing from when x is -2 to when x is 1, in union with when x is 4 to when x moves towards infinity. Now, it's confusing a little bit because you're looking at probably the y value going up to infinity, but that's not what we're looking at. We're looking at when x moves towards positive infinity. Now, decreasing. Hopefully this will help you. It's decreasing from here, but you have to think, what is the x value? It's -infinity, not the y value of positive infinity. It's decreasing from -infinity until x gets to -2. And then it's decreasing again from 1 to 4. So that is the idea behind naming the intervals where a function is increasing or decreasing. All right, the last property that we're going to look at is what's called boundedness. And essentially there are 4 different ways a function can be described in terms of its boundedness. It could be bounded below, which means it has a floor. So let's just say it has a floor to it. It has a lower bound. It has a number that it will never go below. So let's say it looks like this, maybe an exponential function. This function will never go below 0. It just flattens out. So that's called bounded below. Clearly, bounded above would be a ceiling. It has some sort of upper bound that it will never go above. So maybe an upside down parabola would work because it will never go above that number, ever. Now, bounded means it has a floor and a ceiling. So floor and a ceiling. It has a lower bound and an upper bound. So a good example of that would be a sine curve, which we'll talk about in the second semester. But it will never go above 1. And let me put that in a different color. It never goes above 1, and it'll never go below -1. So this is an example of bounded. So you don't say it's bounded above and bounded below. No, you just say this function is bounded. And then, of course, unbounded means it has no floor and no ceiling. No floor and no ceiling. So in other words, let's say it looks like this. Okay? This arrow means it's going up to infinity. This arrow means it's going down to -infinity. So there is no maximum value. There is no minimum value. It is unbounded. And that is how you describe a function's boundedness.